Okay, great. So our second speaker, the title is Automatic Recognition of Hand Gestures for Crane Rigging Using Data Gloves in Virtual Reality, presented by Jochen Teizer from Technical University of Denmark.
Okay, so here we have a video and we are going to play it. It's about the paper you were mentioning.
Hello, this presentation is on the paper for the ISARC 2022 conference, and the title is Automated Recognition of Hand Gestures for Crane Rigging Using Data Gloves in Virtual Reality. My name is Jochen Teizer, and I'm explaining the purpose of serious games. Actually, we all know that in education we tend towards engaging our students much more. This is where serious games come in. They actively involve the students and immerse them in hands-on training. So the more we can do to create learning environments that use gamification, the more rewards and challenges are actually presented to the students that engage them and foster their learning. As in the previous paper we have published a year ago at the ISARC, we have defined what a digital twin would need to look like if one would use virtual learning environments. First of all, of course, we need to use geometrical information. That means 3D models or any products that are existing on a construction site to create this virtual experience. Of course, if we tend towards safety training, the training tasks need to be explained and defined. Here we need to define the processes and the roles of the participants, but also the scenario that the participants need to be in, including the hazard zones, the objects that need to be recognized. Often, virtual reality environments, as we know, are single training environments where one person experiences visual artifacts. This is something we may want to change. And this is where our knowledge comes in, not just from the safety regulations and the project information that we have available. We want to foster and tailor these learning environments towards specific use cases that actually will help the workers carrying out the work safely just before they execute them. This is where we think that training environments can assist, like this one here, where people work near a leading edge or have to climb up a ladder. Whether this is good or not is a different topic, but this is what virtual training environments can look like, where multiple hazards actually exist. For example, the fall from a leading edge. Now, what's nice about virtual reality, it's not just good for visualization, it also allows you to collect data about the participants, the users that actually are in the training environment. And this is something that has not been explored a lot quite yet in our community. Furthermore, we can detect patterns of the users and correct their behavior. And this is something that's important. We want to actually go to active learning environments and provide the users with personalized feedback as much as possible to generate them with situational awareness. And by supplying them with data that's being processed in runtime, I think we have a good chance to actually make that happen. For example, detecting hazards that have previously not been recognized, finding new ways of organizing our work environment and the training environment. And there virtual reality comes in. We can actually build the virtual training environment from a digital twin that's not just there to only visualize, but also predict future states. What tools do we actually have available? In a nutshell, many of you know about that, and I'm just listing here a few of those, and the progress in hardware and software development right now is really, really fast. So some of those actually might be outdated already. And we focus here on the one on the bottom, on hand and finger tracking. There has been several research studies being done on that already, but very few actually in construction. Now, of course, like anybody else, we have made severe experiences with virtual training environments. We call them here PET 1 breaks up and lean construction in VR. We have associated papers to each one of those in ISARC or ConVR proceedings. Please follow up on those. I'm not going to explain those, but they actually were some of the first studies that actually harvest the data that can be collected by the users in these environments. We also have created an asymmetrical multiplayer environment. We introduced it last year at the IGLC, focusing on lean construction, where you have multiple construction workers or equipment operators involved. Like you can see here, a crane operator actually not utilizing virtual reality equipment like a headset, rather sitting on a display operating the crane. And then you have multiple workers, pedestrian workers using an augmented virtuality environment where they actually utilize the angle grinder and turn them on in the VR scene when they press the button. That's something that is also not happening often in virtual reality. And then you have a traditional worker, like a safety inspector, who actually wears the headset and the controls that are typically coming with a virtual reality environment hardware. And this is the issue that we see. Once we have an asymmetrical multiplayer environment, first of all, that hasn't existed before. We've actually seen and experienced that there's trouble of communicating among the participants in the virtual reality. And this is a challenge, if I may say, on a background literature review, that avatars, displaying avatars in a virtual reality environment and having them communicate to each other, like the humans communicating in the virtual reality to each other, is a big challenge. As we play in a typical lean game, a couple of rounds, we see the first time they play, it doesn't work that well. I'm not going into the details. Please read up on our paper from last year. The second time they play, they are much better organized, and according to the location-based schedule you can see here, they have performed much better. However, we still face the issue that communicating among the participants like you would do in a real world, for example, the pedestrian worker actually trying to communicate to a crane operator, please lower the load or move it up, and it's a big challenge. That's where we come in with data gloves. Data gloves actually can simulate very well the hand motions. Actually, you can collect data. I'm not going into the details. There's several providers of these tools available. And here we focus on a couple of those specific hand signals we actually find interesting in the construction environment as they relate to crane rigging. For example, stop the boom, the load, raise the boom, lower the boom, hoist, and lower. So these can be actually recorded, these signals, using this data glove. And you see here some displaying of a hand, the XYZ, the orientation. This can be done using this data glove. I may go back here. Actually, we use the data glove, and on top of it, we actually use an HTC Vive. That actually allows us to track the location of the hand. So how does our gesture recognition algorithm actually work? Well, we create a library of predefined gesture models. That was done in Unity. And based on the finger movement of the data, we can actually assign 3 different types of models. And you may wonder why only 3 if we have 5 different signals. Well, actually thumbs up and thumbs down use the same gesture model. Pointing upwards or pointing downwards is using also the same gesture model. And high five, meaning the stop signal. Yes, once we have generated these gesture models, we actually also generate gesture rules from real-time hand tracking data. This is where the Vive tracker on top of the data gloves come in place, like I mentioned before. It gives us the location, the orientation. And of course, we then associate attributes called transform that contains the position, the rotation, and the scale of the object in the virtual environment. So actually the user, while he is in VR, can actually see how the hand is being moved, or how the fingers are changing depending on the signal they're making. And it's very interesting that the data about the fingers can then be recorded, and of course it's very important to set the tolerance level quite strictly in terms of figuring out actually what specific hand signal is being performed, or in order to recognize it. Coming to the implementation and the results of our gesture recognition method, again, we are here at a very preliminary stage, so we basically have the raw hand movement in real time. We stream it, the data in Unity Live, we record it, and it gets tied to the library of the gesture model. And then the question is whether this gesture is actually in the library or not. And again, here setting the tolerance is really a key. And since our gestures are quite different, those 5 different ones, it's quite easy to separate them as of right now. Yes, and if they're recognized, of course, we end our procedure, but if not, we actually define there is no recognition needed and the search is going on. And at some point, of course, we have an experiment ended. Typically, an experiment lasts for a couple of minutes, going through the different signals and seeing if the algorithm actually works. You can see this here. There's the stop signal. Here's the lower the boom, raise the boom, and so on. About our accuracy, we're quite fine as of right now. We're above 95%, or roughly above 94%. Let me change that. And actually, it works quite fine. Of course, there are situations where you maybe move your hand too quickly and the algorithm is not able to record the hand movement. Of course, we have issues. This is in more detail explained in the paper, where we have raised boom and lower the load. They cause errors and require further attention. In a summary, the preliminary work has shown that active learning environments are rewarding, especially in virtual reality. But again, we go towards asymmetrical multi-learning environments. That's, I think, the key, because not everyone is actually familiar or used to virtual training environments. Some actually experience the virtual motion sickness. And this is an issue where those participants then become kind of participants of the 3D game experiments, like just sitting in front of a screen. Yeah, virtuality can also be used as a source of data and not just only for visualization purposes. I think this is a big change in terms of how we often think and utilize virtuality. And of course, the tools that we utilized here in this study, like hardware, as well as the software, exists. But again, we need to make it user-specific and use case-specific. And I think this is what's nice about our field, that we have applied work where things come together. In the end, I envision this work we are pursuing here to be part of an asymmetrical multiplayer environment where we have multiple players that can actually perform work and communicate well enough with each other. And our purpose and our research objective is to figure out how well do people communicate with each other and which hazards are caused by not communicating effectively. Thank you very much, and I appreciate your attendance.